today we're going to be talking about proving the fundamental theorem of calculus. So to prove the fundamental theorem of calculus, which is, by the way, defined as the integral of a to b of f of x dx equals the antiderivative evaluated at b minus the antiderivative evaluated at a, where the derivative of the antiderivative of f of x is equal to f of x itself. So to prove this, first we must prove three things. These tools will be necessary to do the proof for the fundamental theorem of calculus, which isn't too bad if you can assume these three theorems. So first, the critical point theorem, second, Rolle's theorem, and then the third, mean value theorem. So we're going to prove these in sequential order. So I'm going to start with theorem 1. So theorem 1 states, if f is differentiable at a local extreme point, I'm going to call it mu in d sub f, which is the domain of f, then f prime of mu must equal to 0. So first recall the extreme value theorem that states if a function f is continuous on a closed interval a to b, then f has a maximum and minimum value that resides in the interval a to b. And then the proof goes as follows. So first I'm going to suppose f is differentiable at mu in the domain of f, right? That's what the theorem says. So we must show f prime of mu equals 0. So without loss of generality, I'm going to say let mu be a maximum point. And so if I were to do the minimum case, it would be done in the same exact way. So therefore, by the extreme value theorem, I'm going to say EVT, there exists a delta sub 2 greater than 0 such that for all x in the delta neighborhood of delta sub 2, of mu, so the delta sub 2 neighborhood of mu is what I meant to say, and d sub f. So this is actually an important point. So we're saying there exists a delta sub 2 greater than 0 such that for all x in my delta sub 2 neighborhood of mu and for all x in d sub f. That's important. This implies f of x is less than or equal to f of mu. So notice here that we don't necessarily, the neighborhood of delta sub 2 and mu doesn't have to reside in the domain of f. So we have to consider that, and that's why we're going to need another delta neighborhood to account for that, case. So let me go to the next page. So what I'm gonna do, I'm gonna say is also let delta sub 1 be greater than 0 such that our neighborhood of delta sub 1 of mu is a subset of d sub f. What that means is we have this delta sub 1 neighborhood of mu such that it's always all the elements in that neighborhood reside in the domain of F. So what I'm going to do is let delta equal the minimum of the two. So delta sub 1 and delta sub 2. Therefore, we have f of x less than or equal to f of mu for all x in the delta neighborhood of mu. Since the delta neighborhood of mu is in the domain of f, and every element in the delta neighborhood is less than or equal to f of mu. From this, if I were to subtract f of mu to both sides, I say so f of x minus f of mu is less than or equal to 0. So let me illustrate the idea of those two delta neighborhoods. So let me just write some arbitrary function here. Just draw it real quick. So we have, let's say, a function that goes up like that, goes down like that, maybe that goes up like this. And we'll say maybe stops right here. We could say that this is A, and this is B. So just by inspection, I can see that the maximum point would be right here. So I'm going to call that f of mu. And then that's mu. So let's say I pick our first delta 1 to be here, and then so that would be the left endpoint. So let me write. So let's say n delta mu would equal mu minus delta 1 to mu plus delta 1, right? So it's an open interval. So if this is the left endpoint, the right endpoint would be, let's see, about right here. So we can see the problem that the function is not defined over here. So from here to here, we have elements that don't exist in our function. So to account for that, I'm going to pick another delta, delta sub 2, and we could say is from here to here. We could see if that's the case, then clearly delta and delta sub 2 of mu resides in the domain of F. Oh, I'm sorry. I got them mixed up. This should have been delta 2. And this should have been delta 1. So let me just reiterate that real quick. So we have this function here with a maximum point of mu. If I could choose all the elements of x in this delta 2 neighborhood such that mu would be a maximum value. But the problem arises where we have elements in the delta 2 neighborhood that don't exist. So what I do is I use another neighborhood that's a subset of the domain F, and then I take the minimum of the two deltas. So if you take the min of the two deltas, and I call that delta, and I use that as my neighborhood, I get a condition where all the elements in that delta neighborhood are satisfy the inequality of f of x less than or equal to f of mu, and all the elements in that delta neighborhood reside in the domain of f. So hopefully that makes sense. So now that I can assume that f of x minus f of mu is less than or equal to 0, what I want to do is I want to consider the limit, right? Because it's differentiable, the precise definition of a derivative is this. So that would be essentially f prime of mu, right? So since the derivative exists, the limit must exist. So what I want to do is I want to consider the left-handed limit and the right-handed limit. So first, considering the limit approaching from the right. I could see that f of x minus f of mu is always less than or equal to 0. So that would be a negative value divided by x approaching mu from the right, which would be a positive value. So that would always be, this limit would always be less than or equal to 0. Now, considering the left-handed limit, where x approaches mu from the left, we have, let's see, f of x minus f of mu over x minus mu. We could see that, again, f of x minus f of mu would be less than or equal to 0. And then x minus mu would also be less than or equal to 0. So this inequality would actually always be, or this expression rather, would always be greater than or equal to 0. So remember, for the limit to exist, the left-handed limit and the right-handed limit must be equivalent. So the only case where that would hold is where they're equal to 0. So therefore, the limit as x approaches mu of f of x minus f of mu over x minus mu equals 0. So, because remember, we assume the limit exists. So that's the proof. So this means f prime of mu equals 0. So that was theorem 1. So theorem 2, that's Rolle's theorem, states that let f be continuous on a to b and differentiable on a to b. And then we're also assuming that f of a equals f of b. In other words, the endpoints a, b are assumed to have the same function values. So if we're saying if that those conditions hold, then there exists a mu in the interval a to b, but not including a to b, such that f prime of mu equals 0. So if I consider the case where f of x equals c, where c is in the real numbers, for all x in a to b, we're done, right? Because the derivative of a constant is 0. So that's one case to consider. Okay. Otherwise, if that doesn't hold, since f is continuous, I can use the extreme value theorem. There exists a max and min by the extreme value theorem. So I'm going to say let m, little m, be the min of of f of x such that x is in A to B, and let capital M equal the max of f of x such that x is in A to B. So there's some element in A to B such that we have a max and min, where either M, capital M, does not equal f of A, or, sorry, little m does not equal f of A. And that's the same thing as f of B. So it's possible that the minimum or maximum value could equal f of A, which is the same thing as being equal to f of B. So we're saying one of them doesn't have that. Since f is differentiable, on A to B, this implies either f prime of x1 equals 0, or f prime of x2 equals 0. And what I mean by x1 and x2, I mean some element x1 that gives you the minimum value and some element x2 which gives you the maximum value. So let me write that f of x1 equals m, f of x2 equals capital M. So what we're saying is, since f is differentiable, we can assume, and since we know we have the extreme value theorem, we can use theorem 1 to assume that there exists a point x1 or x2 such that the derivative of the function is equal to 0 at that point. So that's the proof for that one. So theorem 3 is the mean value theorem. That's a very important one. That states that suppose f is continuous on A to B and differentiable on A to B. Then there exists a mu in A to B such that f of B minus f of A over B minus A equals f prime of mu. So the way I'm going to do this proof is I'm going to first assume f of B is greater than f of A. So that's without loss of generality. You could assume the other way around. It won't make a difference. So since f is continuous, on A to B, there exists a mu in A to B such that f of A is less than f of mu, which is less than f of B. What I am going to do is I'm going to pick a function, I'm going to call it h of x, that satisfies the Rolle's theorem. So I'm going to say let h of x equal f of x minus f of b minus f of a over b minus a times x. So this seems like a bit of magic, but there is some thought process to this, right? So we're picking a function that's in terms of f of x, right? So if we recall from Rolle's theorem, we need two conditions. Number one, we need it to be continuous on the interval a to b and differentiable. And we need the endpoints to be equivalent to assume Rolle's theorem. So what I'm going to do is I'm going to see, hey, is that satisfied with h of x, right? So what I'm going to do is I'm going to go to this screen and we'll see if that makes sense. So h of x equals f of x minus f of b minus f of a over b minus a times x. So clearly it is continuous, right? So f of x is continuous, that's assumed. And then any product of just x alone is a linear function, which is also continuous. And then we know the sum or difference between two continuous functions is also continuous. So it is continuous. It is also differentiable. Again, f of x is assumed to be differentiable. And any linear function is differentiable as well. And then the sum or difference of any two differentiable functions is also differentiable. We can assume that. So 3, does f of a equal f of b? Well, we need to validate that before we can assume Rolle's theorem. So let's check. So that's going to be a little bit of algebra to validate that, but it can be done. So let's consider h of b. So h of b is equal to f of b minus f of b minus f of a over b minus a times b. Now what I'm going to do is I'm going to get common denominators for these two terms. So in essence, multiply f of b and then the denominator by b minus a. So that's going to look like this. And then I'm going to distribute the b in here. Okay. So distributing the minus sign and combining and distributing the f of b, what we get is this. It's minus b f of b plus b f of a, distributing that minus sign over the quantity b minus a. Okay. Let's see. Notice how these two terms cancel out. So what we get is b f of a minus f of b a over b minus a. So that's our expression. So that's for h of b. Now let's see what we get for h of a. So I'm going to write h of b equals that, and then I'm going to erase this part over here and see if we get the same thing for h of a. And if we do, we know we can use the Rolle's theorem because the three conditions are satisfied to use it. So, almost done. Okay, so let's see, h of a is equal to f of a minus f of b minus f of a over b minus a times a. So this is done same way. Multiply b minus a numerator and denominator here. Distribute the a. So we get f of a times b minus a over b minus a minus a f of b plus a f of a over b minus a. So this is just simple algebra. So we distribute that f of a. We get f of a b minus a f of a minus a f of b plus a f of a over the whole quantity b minus a. So we do have terms canceling out here. You can see here this guy and this guy cancel out, and we're left with b f of a minus a f of b over b minus a, which indeed is the same as this. So we can indeed say h of a equals h of b. Therefore, we can assume the Rolle's theorem. So for all that, we set our function h of x equal to f of x minus f of b minus a over b minus a times x. And I say, okay, well, h of x has the three conditions, or satisfies the three conditions for the Rolle's theorem. So I could say, by Rolle's theorem, there exists a mu in a to b such that h prime of mu equals 0. So first, note that h prime of x equals f prime of x minus f of b minus f of a over b minus a. So right there. So therefore, h prime of mu equals f prime of mu minus f of b minus f of a over b minus a. And we know that's equal to 0, so equal to 0. So now add the term f of b minus f of a over b minus a to both sides of the equation, and we get f prime of mu equals f of b minus f of a over b minus a, which satisfies our condition that there exists a mu in a to b such that this expression holds. So we're done. So that's theorem 3. So now we've proved the critical point theorem, the Rolle's theorem, and mean value theorem. And we're going to use those tools now to prove what our goal was to prove this whole time, which is the fundamental theorem of calculus. So fundamental theorem of calculus officially states, suppose f is integrable on a to b, and that capital F prime of x equals little f of x. So capital F of x is the antiderivative of f of x. Then the integral of a to b of f of x dx equals the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. So the proof goes as follows. What we're first going to say is, since f is integrable on a to b, all epsilon greater than 0, there exists a delta greater than 0 such that our max of our delta x i's less than delta implies that our partitioned Riemann sum minus our integral is less than epsilon. And that's from 1 to n. So if you're unsure what I'm talking about here, this is the condition of Riemann integrability. It's how we assume an integral exists. I made a video briefly covering Riemann integrability. So if you're unsure about that, look at that. So what we can assume here is that number one, capital F of x is differentiable, right? And also continuous. So what I'm going to say is, since capital F of xi is differentiable, and continuous on A to B, there exists an xi bar that resides in xi minus 1 to xi, such that f prime of xi equals f of xi minus f of xi minus 1 over xi minus xi minus 1. So what that is the mean value theorem, right? So what I'm going to do is I'm going to multiply the denominator to both sides. So we get f prime of xi times xi minus 1 equals capital F of xi minus f of xi minus 1. So also note, like that, erase that. So I want you to also note, based off our assumption in the beginning, f prime of xi equals f of xi. So essentially, what we could say is f of xi times, let me use xi bar. So f of xi bar equals, so capital F prime of xi bar times xi minus 1 equals f of xi bar times xi minus 1. And then we also know, based off this here, that's equivalent to capital F of xi minus capital F of xi minus 1. So what that means is we have this sum here, f of xi bar times xi minus 1 from 1 to n. And we know that's equivalent to f prime of xi bar times this difference here from 1 to n. And then from there, by the mean value theorem, we know that's equal to capital F of xi minus f of xi minus 1. Now, what this is going to equal to is you're going to have terms canceling out except the endpoints. So this sum would actually just be equal to this expression here, capital F of xn minus capital F of x0. So if you recall, I defined in my first YouTube video that xn equals b and xo equals a. So that is equal to capital F of a minus, I'm sorry, capital F of b minus capital F of a. So that implies that f of b minus f of a minus our integral is less than epsilon, right? We just rewrite that because our original condition of Riemann integrability is equivalent. So this implies f of b minus f of a approaches our integral. Therefore, capital F of b minus capital F of a equals the integral of a to b of f of x dx. So, done. So just to recap real quick about what we did here is we first assumed the condition of Riemann integrability because the integral exists. We considered capital F of xi bar. And we said that's differentiable and continuous on A to B. Therefore, by the mean value theorem, this holds. From there, we were able to obtain an expression that allowed us to substitute into our sum a new expression. And that came out to be capital F of b minus capital F of a. So therefore, the antiderivative value of b minus the antiderivative value of a is equal to our integral from a to b of f of x dx. Thank you for watching and have a good day.